In your text, the beginning of the chapter describes an archaeologist who's come across a dinosaur bone. She begins this quest by going on a systematic search using her tools, her dental pick and her brushes. And as she's poking and working away at moving the dirt, she makes an observation and she carefully documents what she sees. She takes pictures of it, and eventually, as she makes these observations, she realizes that she has made a wonderful new discovery, a set of dinosaur bones. Can you imagine how exciting that must have been for the researcher? When we discover something, it usually means that we're gaining knowledge about it for the first time. The focus on the discovery approach to learning, that is the topic of this textbook, uses the concept of discovery in that the students will actually be engaging or practicing science rather than just learning about the science secondhand. And in this way, they will develop a deeper understanding not only of the content but also of the scientific practices along the way. We have to remember that learning is what's called an iterative process. It's not something that happens suddenly, and we should resist the urge to try to make our students learn or discover everything that there is about a topic at once. Their learning and deeper understanding will be built over time. As their teacher, when you teach an elementary student science, you have both both an enormous responsibility and an incredible opportunity to lay the foundation for your students to learn to think like scientists. You're going to set them on a path to where they can start learning how to um, engage in critical, evidence based thinking. And that is the foundation of scientific and engineering ways of knowing. So now we're going to talk about Chapter 3, Science Practices and Inquiry Processes. So how do we actually go about the process of designing our courses to where we can incorporate inquiry processes and let the students be engaged in scientific learning practices? The beginning of your textbook talks about an archaeologist as she's going through a dig. She has her tools. She's brushing the dirt away. She comes across something that looks like a bone, and she starts to get more excited, and she starts to um, the beginning of chapter 3 describes an archaeologist as she's out searching for bones, and she's thinks that she's come across something new, and so she gets excited and she starts brushing the dirt away gently, and she takes her time and she starts to go through the process of using her tools to carefully uncover what's underneath the dirt. The more of it that she uncovers, she soon realizes that it is the toe of a brand new dinosaur, one that she's never seen before, a newly discovered dinosaur bone. She has gone through the process of careful observation, and she has made a exciting and extraordinary new discovery. Can you imagine how exciting that must be? As teachers of young children, we have the opportunity to provide the same level of excitement and discovery in our classrooms to help our students to learn and uncover new information, to build on their knowledge. And it is through this process of discovery based experiences that we can design the types of activities that will enable them to be able to go through the practice of science to uncover and observe and discover new things and thus build on their knowledge. So your entire textbook is going to build on the idea of discovery. So, simply speaking, discovery means just learning something or coming to know something that we did not know before. You are going to learn about discovery in a way that you're going to learn to engage your students in the discovery process by, like I said, getting them involved in practicing the science, in doing the science, and actually getting involved in discovering their own knowledge, uncovering their own information to build their knowledge rather than just learning secondhand facts and memorizing them from other sources. They're going to be active participants in building their own knowledge. This is going to enable them a deeper understanding of the concepts and topics that we are going to be teaching them. We have to keep in mind that learning science is something that takes place slowly. It's something that it's iterative. It builds on fundamental knowledge, and it is a process that is ongoing for a lifetime. And so, as a new instructor or as an instructor of a young child, it's going to be important for you to resist the urge or the temptation to try and have the child to discover everything that there is to discover about a topic all at one time. You're going to want to let their learning progress naturally and steadily. You, as the elementary teacher, have a tremendous responsibility, but also a an incredible opportunity because you are going to be setting the foundation for these kids on which they're going to learn to think like scientists. And I know you're tired of hearing me say that, but it is true. I want to get it to where that is just the thing that you think about all the time. It is my responsibility to build a foundation in my children to where they don't just know scientific facts, but they are able to learn the practices and skills that will enable them to be able to think like scientists. You want them to be able to think critically, and because that is the basics, that is the basis of science knowledge. When we use discovery in our classrooms, just like the archaeologist who was uncovering the dinosaur bones, we are going to be giving them their own little set of, quote, tool packs that they're going to be able to use in their own personal discoveries. And we're going to be guiding them through that discovery. They're going to be able to, through these discoveries, they're going to develop their own set of values and ideas, and they're going to construct their own knowledge and their own principles and their own attitudes that will help them as they go out into society, as they grow up into productive young citizens of the world. It is going to be important that we respect the individual student, the individual child as an individual, and understand that each one of them is going to come to us at a different level with different sets of prior knowledge, with different sets of barriers, with different sets of gifts, with different sets of limitations. And it's going to be our job to meet them where they are and to provide for them their own personal learning experience. As a teacher, we cannot learn for our students. We're going to have to lead them to forge their own understanding about the topic. We're going to be there for them to guide them, but it is our role to provide the experience. Our major role is designing the activities, designing the experience that the children are going to actually gain. We're designing the experience that they're going to go through which they will be asking the questions, finding the evidence, and making the discoveries and constructing their knowledge. So as you see, this is it goes along with what we learned in chapter 2, that supports the constructivist strategy, because this path to discovery enables the child to build his or her own understanding. So how do we do it? How do we make discovery learning a central feature of every course that we teach? Discovery is not going to happen just because you let students do some fun activities. When you teach them science, you're going to be preparing their minds to make discoveries. Discovery learning happens when a child's mind uncovers new information, makes new connections, and comes across new insights that deepens his or her understanding. And this is an individual and personal experience. They need to get new knowledge that's meaningful and that adds to their existing knowledge and deepens their understanding, and in many cases replaces their common misconceptions that they previously held. In the process of discovery, explanations are sought that are based on observing something, gathering evidence, and then thoughtfully reflecting on the observations and the evidence. And so, as their teacher, you are going to create the learning experiences that allow them to make the connections between their observations and the evidence and the questions that they have. Your job is going to be that they make honest connections and that deepen their understanding and their experience as their knowledge grows. As a teacher, you're not just giving them the opportunity to discover, you're also teaching them how to discover. You're guiding them through how to ask the right questions, how to collect the right evidence, how to observe properly, to make the right observations. So your charge is going to be crafting the activities and learning experiences, and then interacting with the students to guide them to develop the intellectual and physical tools that are necessary to look for the explanations through the process of discovery. You're going to be providing the hands-on, mind-stretching experiences that are going to enable the kids to use their knowledge and skills in a way that build on the knowledge that they already have, and that also will connect with the set of knowledge that they will be gaining in the future. In your text, the author describes the fear that he experiences with many teachers who fear that their classroom is going to be thought of as a circus if they're just kids in there just doing activities and loud and talking. And he describes that discovery learning should be filled with excitement. The students will be talking to each other. They may be animated. They may argue. They may be asking each other questions. They may be wondering. They may be testing ideas. And if they're doing so in the context of the science problem that you have and the science activity that you have posed to them, the challenge that you have posed to them, then you have accomplished your task. It may look to the untrained eye, to someone who is not well versed in pedagogy, that this is an out of control classroom. But for those who truly understand what constitutes learning for the science student, then they will truly understand. Now, this activity filled buzz will also be followed by periods of downtime. They're not always going to be playing. They're not always going to be engaging in hands-on activities. Many times they're going to be reflecting on their data. You're going to be talking with them. They're going to be writing about it. They're going to be answering questions. They're going to be thinking about it. So you're going to be designing your activities so that there are periods of of dynamic activities and energy filled activities, and then there's going to be time when they're quiet and they're able to sit down and process and reflect. There also should be times when they have the opportunity to quietly and speak. Should I say? Exchange their findings and their ideas and talk to the other students and exchange their findings and information and questions and ideas with their students. I'm sorry, with their classmates. And that will build their ability to communicate, that will build their critical thinking, that will build their analysis and assimilation skills. And it also will build the students' confidence in the scientific thinking process. There is nothing accidental about the teaching process. There's nothing accidental about what you're going to do when you walk in that classroom. You're not going to just walk in there and put something down on the table and let them start playing. You have to have well planned out activities. Your activities should coordinate with the content, knowledge area, or skill that you're trying to build with the students. For example, your textbook gives an idea, your textbook gives you an example that although building my mind is going blank. Although building a model volcano may be a fun activity, it's not as effective as a teaching strategy or a discovery based strategy unless you connect it with building it around the concepts of heat and energy first. So, when you have the activity, you have to connect the activities with the underlying contact, context, content, and scientific principles that you expect the student to learn. And so, therefore, it's very important when you select your activities or design your activities, you do so carefully, and you identify targeted learning outcomes for the activities, and make sure that the activities address your targeted learning outcomes. So, in the last chapter, we said that when we are seeking discovery, when we're trying to make discoveries, we do so through a process called inquiry. And I know that you've probably heard this word quite a bit in your studies as education majors. And if you are aiming to teach science, to be a science teacher, you probably heard it even more because it's even more commonly used in the science education community. The inquiry approach, the simple definition that your text gives, is the careful and systematic method of asking questions and seeking explanations. And to guide our students through inquiry based learning, where we expect them to formulate questions and guide them through those questions to going through the activities and seeking evidence and finding their own explanations to questions. There is a systematic framework that we're going to use to guide them through that process. When we use the term systematic, we are not implying that it's the only way that the process can be done, but moreover, what we're saying is that it's a carefully planned out way in order to collect valid information that can better explain something or answer a question or solve a problem or to help us to create a new or improved design. When we're collecting evidence, what is that? Evidence is data, and data can be measured, either qualitative or quantitative. When we evaluate our evidence, it either will support or not support our proposed explanations for something. As we make advances in science and engineering, all of these advances, all of the new information, all of the new explanations are based on evidence. I hope that you've purchased the access card to the textbook. There's a video in this chapter of an inquiry learning experience where the teacher is interacting with the classroom, engaging in an inquiry activity. And I encourage you to watch this video and observe what is the teacher doing, what are the students doing, and think about what the evidence is that makes this activity an inquiry-based learning experience. That's something that I strongly encourage you to do on your own. So in thinking about inquiry, we can think about it from two different perspectives. When a student is learning through inquiry, that means that the student is constructing the knowledge through the process of asking the questions and seeking the evidence and formulating the explanations that are based on this evidence and justifying their explanations. That is learning through through inquiry process. A student who's learning to inquire means that the students are consciously applying the processes that are associated with inquiry. Okay, so learning through inquiry means that they are constructing knowledge through the process of asking the questions, gathering the information. Is the knowledge that they are constructing. But when they are inquiring, it means that they are applying the process associated with inquiry as a part of their thinking strategy. Okay, so they are learning to ask questions as a part of the strategy that they're applying to their overall approach to learning. Another point of clarification that needs to be considered is that there are different degrees to which inquiry is practiced in the classroom, and different degrees to which the teacher will have different degrees of control over the inquiry process. So, in a process called guided inquiry, the teacher is more in control over the types of questions that the student is guided toward. So, the teacher is there to help guide the students toward asking a certain type of question. In open ended inquiry, the students decide all on their own what questions will be asked and seek their own hypothesis, seek their own evidence, etc. Now, as we move through the next few slides and we actually describe the inquiry process, your textbook makes the distinction that science and engineering are going to be used interchangeably unless otherwise specified. And remember from chapter 1 what the distinction between science and engineering is. Science is the body of knowledge and the process of thinking toward toward acquiring that body of knowledge. Technology was the application of science, and engineering was the design of the technology. So basically, your textbook is using science and engineering as both processes. So those things are going to be used interchangeably unless otherwise specified. So when you hear me talk about science and engineering, I am speaking about the practices in the learning community. Remembering what we said was our basic definition for inquiry, of a way of asking questions to find explanations to the things that we want to know. So you're going to engage in scientifically oriented questions. You're going to look at the evidence in responding to those questions, you're going to formulate explanations from that evidence, and then you're going to connect the explanations to scientific knowledge, and then you're going to communicate and justify the explanations. Some examples of inquiry methods would be to review what's already known, that's things that are already known based on new experimental evidence. Using tools to gather, analyze, and interpret data. Proposing answers, explanations, and predictions, and then communicating the results. And another one is identifying assumptions, using critical and logical thinking, and considering alternative explanations. So now let's look at science and engineering practices. And remember, a few minutes ago I told you that these two terms are going to be used together. What's the first thing that we have to do in the process when we start putting this into practice? Well, it just makes sense based on what we know to be the definition of inquiry, which is asking questions to find explanations. It makes sense that our starting point is going to be to ask the questions or define the problem. So, knowing the problem and asking the questions is our fundamental starting point. As in science, the question usually is based on trying to understand a phenomena. And your book gives as an example, why does my dog walk in circles before it lays down? How do turtles find their way back to their birthplace? So something that they observe in nature that is a fundamental phenomenon that they seek an explanation to defines the key question. On the other hand, engineers, they start out by a problem, something that needs to be solved. Why? How can I make a product less dangerous? Or how can I make cars get better gas mileage? And the kinds of questions that we want to ask are those that can be answered using evidence that we collect from direct observations, such as how do hurricanes form? And these can be investigated by the collection of data. We should not have the questions that are based on values or opinion. They are not usually good scientific questions. For example, is basketball a better sport than swimming? That's not something that data can support, because my data might be biased when I generate it based on my personal beliefs or my opinion. So we're going to talk a little bit later in another chapter on strategies for asking students questions. In this chapter, we're focusing on the types of questions that we want them to learn how to ask. And we basically will we'll teach our students to ask the questions that fit into one of these four categories. Information seeking questions, wonderment questions, how does it work questions, or how to solve problem questions. And so we're going to look at each one of these right quick in detail and explain what each one of these means. Information seeking, wonderment, how does it work, or how to solve the problem. So information seeking questions are just what they sound like. They're questions that are designed to gather more information about something. When you need more facts about a system, many times the information is available and students can, go and look it up someplace. But often this presents a great opportunity for them to be able to use direct observation to gather the information. They can use a model object that they can observe and describe what's happening in order to get the information that they're seeking. The next one is wonderment questions. When a student asks himself, I wonder what will happen if. And so this type of question suggests a proposed relationship between two variables. For example, what would happen if I use two batteries instead of one in a circuit? And if the student makes a prediction that the light will get brighter and then tests her prediction to confirm or falsify her prediction, she's doing science. How does it work questions. How something works seeks explanations. How do volcanoes explode? That's a science question. That's a science-centered question. How does a solar panel work? That would be more along the lines of an engineering question. But this gives great opportunity if the teacher takes advantage. Instead of immediately going to look something up, these type of questions provide an excellent opportunity for real inquiry. For example, your book gives a scenario where instead of providing the answer to the student why the seasons change or looking it up online, they can actually participate in an activity where they track the movement of the sun over the course of a few months. They then would generate their own evidence that they can use in order to develop their own explanation, and then they can test their hypothesis or test their explanation and communicate it and compare it with others, and that is doing science. The last one is the how to solve problem question. This question is at the heart of engineering, and many times it leads to us modifying products or designing new products to solve a problem. And this is a excellent opportunity also to engage students in inquiry, to help them to learn about the process of engineering, to learn that the design phase is never finished the first time. It's an iterative process where they design, they build it, they test it, they analyze it, they redesign it, they build it, they test it, they analyze it. For example, if there's a problem that the students identify, that the book gives you an example of, I think that let's see, how to make a bird feeder squirrel proof, or how to make an automatic feeder for the class gerbil, or something like that. So if it's an application of technology that you're trying to get your students to consider how to solve that problem, you can guide them through the process of designing something that's based on an idea that they may have, and building it and testing it and analyzing it. And you may be surprised at the ideas that some of the students come up with. This is the soil in which the seeds are planted for great scientific thinking. You just never know what you may end up sparking or or igniting in a child's imagination with these types of activities, and leading them through these types of inquiry-based questioning exercises. Okay, so these are the questions that we want to get students to learn how to ask. Remember, these are the questions that we're guiding them through, and our strategies as to what we're going to do in the process, how the the activities, the behaviors, the what the teacher is going to be expected to do in the inquiry process, and in the instructional design process, we're going to talk about in later chapters. But these things are the things that we expect the students to start to do in the inquiry process. And the first is the questioning. And I just went through all the 4 different types. Okay, let's continue with science and engineering practices. The next thing we want to consider is developing and using models. What is a model? A model is a representation of the system or phenomena that we are interested in. A model can be in the form of a diagram or a 3-dimensional model, a computer simulation, a mathematical representation, or an analogy. Models help us to visualize what's happening in a system. Your book gives an example of using a lamp and a globe to model the behavior of the earth and the sun. And although the model will have limitations inevitably, it helps the student to be able to mentally conceptualize something better. Of course, we know that the scale of a lamp and a globe would not be accurate, but a model is a great starting point for understanding the relationships between the components of a system that we're trying to understand. In science education, we hope that students will use the models to represent the understanding that they have, and as they go along, we hope that their mental models and the models that they use will go through an iterative process every time new evidence comes in, every time they get a deeper understanding. We hope that their mental models will change. The models that you can expect them to begin with are inevitably more crude than the ones that you expect them to end up being able um, to draw. If you ask them to draw a picture of a process in the beginning of a unit where their understanding is more limited, you would expect that drawing to be much more crude, much less accurate than you would expect it to be at the end of that unit, where you would expect it to be much more precise after the child has learned more about the concept. Planning and carrying out investigations. It seems like a lot to ask for at this stage in their development, to expect a child to be able to plan and carry out an investigation. It's sometimes a process that even the best scientists struggle with, but it is once again this very critical point in their development that you could actually begin to help form these skills at an early age and form this foundation as well. And so, in helping to teach a kid how to plan to carry out an investigation, all we're aiming to do is to help them to identify what should be investigated, what kind of data that we'll need to collect, how to organize the data, and how to analyze it. So if they can identify at this stage what what needs to be investigated, and in order to do that investigation, what kind of data do we need to collect, and how do we organize it, and how do we analyze it? That's a mouthful, I know, but hopefully we can look at some key strategies in future chapters when we actually start looking at some of the science units that will help to be able to connect some of these things for you to seeing how you can actually implement these kind of things in your classroom. Analyzing and interpreting data. Even at this stage, we're going to want to introduce the kids to learning how to analyze and interpret their data. Their it's going to have to be some creativity on your part to help the students to learn to put their data into recognizable patterns. You can help them to learn how to create tables or graphs or diagrams. Your book gives you an example of using square floor tiles to represent bar graphs when describing plant growth. I mean, so you can get very creative with this. And once again, once we get to our actual science units, we're going to be able to see some examples of how all of this stuff can come together to help you to be able to develop exercises, activities, and, and experiences for your students. What about math, mathematics, and computational thinking? This is an area that has made so many people dislike science. Math is one of those things that um, is is a necessary evil. It's not evil at all, but a lot of people are turned off by it, and it has prohibited many people from science, especially the more mathematically intense sciences like your chemistries and your physics. It is just sometimes intimidating to people, but it doesn't have to be. Incorporation of math into your science courses can be just as simple as counting, or it can be more complex. And here we can harness the use of technology. There are so many different programs available that can help us with giving our children an appreciation of mathematical relationships. The graphical relationships, slope, all these types of relationships are much easier to explain with the advent of new technologies. At the end of the day, we aim that the students can construct explanations in science, and if we're talking about engineering, we aim that they can design solutions. Um, If they ask good scientific questions, if they plan and carry out their investigations, if they collect and analyze their data, then at the end of the day, their efforts should end up culminating in them having generated an explanation that is based on their evidence. That doesn't mean that the explanation that they've come up with is the correct explanation, but it means that they will have correctly applied the process of scientific thinking in and inquiry in arriving at their explanation. And we're going to learn in chapter 4 and 5 what the teacher's responsibility will be in guiding the student toward going back to the process to actually get to the correct answer if indeed they did get the incorrect explanation using their experimental data. But this process is very important for them to go through, and the more and more that they do it, the better and better that they're going to get at it, and the more and more they apply it, the more often their outcomes and their explanations will be the correct answer. Now, that was the discussion of the science side. So what about the discussion from the engineering perspective? From the engineering perspective, the goal is to design a solution to a problem. And so there are so many different activities that the students can participate in that enable them to be able to apply what they know from their science knowledge to design solutions for problems. We're going to see potential applications and potential activities that we can do with science and engineering, like I said, for many of the other things that we talked about. We're going to see some of these once we start actually talking about the science content in units 2, 3, and 4, and that will be chapters 10 through 18. Continuing our discussion about science and engineering practices, What about the engaging in argument from evidence? When we think about the term argument, we think about it with the negative connotation. But when we actually argue from the perspective of comparing scientific evidence and developing better understanding about our position or our explanation about something, then it's not a negative concept at all. When we take the evidence that we have and we speak with our peers about it, and we describe the evidence, we discuss it with them, and we argue it. Basically, we ask the critical questions. We evaluate it very with great skepticism, and it enables us to be able to pull out things and discoveries and questions and think deeper and gain more critical understanding than we would have been able to gain without that discussion. And so in our science classrooms for children, sitting around in a circle is a good exercise for them. We can let them talk to each other to not argue. We don't want to teach them to argue, but we want them to exchange information and ask each other questions and teach them how to support the claims that they make, present the evidence that they have for their claims, and ask the other students to learn how to critically ask questions about that evidence. It's a very powerful way to develop their communication skills and also to help them to learn how to deepen their understanding about the scientific the process of science learning. We also want them involved in obtaining, evaluating, and communicating their information. So even at this early age, we want the students to be involved in gathering the information and the evidence, evaluating it, as we've said so many times already, and communicating it, and either communicating it by methods that are similar to the way that we just described above, which is talking to their peers about it, or by writing about it, reflecting about it, journaling, writing a song about it. I mean, there's so many different ways that you can creatively get young students involved in communicating about their scientific discoveries and thereby deepening their knowledge and understanding. All right, so the last thing we're going to talk about in Chapter 3 are inquiry skills. Do you remember from Chapter 1? I truly hope you do, about what science is. It's the process of seeking explanations that are based on evidence, in addition to being the collection of the body of knowledge and the values and attitudes that we hold true. Well, in seeking evidence for that body of knowledge, we use a certain set of skills called inquiry skills. And these skills line up to three different types of descriptive models. The inquiry skills line up very nicely with the descriptive model, the explanatory model, and the experimental model. And these three models, the descriptive model, the explanatory model, and the experimental model, are what we know as the phases of the progression of inquiry. Inquiry. I hate that word because it comes out of my mouth so weird. But as inquiry progresses throughout its phases, it goes through description, explanation, and experimentation. And so the skills that are associated with each one of these processes are going to be described in the last section of this chapter. So let's talk about the descriptive model. The descriptive model uses process skills that such as observation, observing, using space and time relationships, numbers, questioning, classifying, measuring, and communication. So what's meant by each one of these? Well, to observe means to use the senses to obtain information or data about something. This is the most basic process of science. So we are using our senses. We are seeing, we are hearing, we're smelling, we're touching. Hopefully we're not tasting, but maybe we are. It depends upon what the the object under study is. If it's a chemical, of course, we're not going to be tasting. But we're using our senses to collect information or data about an object or an event. Active observation is not the same thing as passive looking. An active observer is going to be using fundamental questions of inquiry. They're going to be looking at trying to describe what are the components or elements of the system, the properties, the background, and interactions among the components of the system. Remember those from the last chapter? What about using space-time relationships? Objects all occupy a place in space. So we can use inquiry skills to describe or determine direction, arrangements in space, motion, speed, symmetry of something, or its rate of change. Classifying. Oh, I skipped one, didn't I? Using numbers. Okay, so we use numbers to manipulate measurements, to put objects in order, and to classify objects. And it depends on the amount of time that you use on describing the numbering system or using numbers will depend on the grade level of your students and the level of the um, the level of emphasis that your school places on math. Okay. Questioning is also a part of this model, and we've already seen questioning earlier in this lecture. What about classifying? Well, classifying allows us to put things in categories or order. It allows us to be able to draw relationships and show similarities and differences among our data. All right. So what about measuring? So measuring is a way to quantify our observations. It's a way to assign quantity to something. We can measure length, area, mass, volume, temperature, all sorts of different types of properties of a system. We can teach our children the relationship between these measurements and how we can use these measurements in our calculations in the descriptive model. Okay, and lastly in this one is communication. And as we've talked about in the earlier parts of this lecture, clear and precise communication is essential to scientific work. Reporting scientific data incorrectly can have some very undesirable outcomes and consequences. And it is important to start training kids at very young age that the communication of scientific data is very, very critical, a very, very critical component of their process. And so in your classrooms, you're going to be teaching them different types of communication, both orally with written words. You're going to teach them to use the diagrams. You're going to teach them the use of maps, graphs, mathematical equations, and other visual demonstrations as appropriate for the activity and for their grade level. So with every one of these components of the descriptive model in your chapter, chapter 3, let's see what page is this on, page 45 and 46. After each description of each individual part of the model, there are some sample activities that the author shows that a teacher may use to understand the way that this model may be used with students in the classroom. So the next set of process skills is the explanatory model, and this model builds on the one that we just described with the descriptive model. It is consistent upon two components, inferring and hypothesizing. Inferring uses logic to make assumptions. It's very important to understand the difference between inferring and observing. When you observe something, you use the senses in order to describe something. And inference is an assumption that you make that is based on that observation. Hypothesis. Okay, hypothesis is a proposed relationship. What do we think a proposed relationship is that explains a phenomenon? Okay, for example, one might hypothesize that butterflies prefer yellow flowers. On the other hand, a prediction serves as the basis for doing experiments. We predict something based on our hypothesis. And so the prediction based on this hypothesis would be that if butterflies are presented with yellow flowers and white flowers, then the butterflies will land on the yellow flowers. Okay? So do you see that? A hypothesis explains a relationship. We think that there is a relationship between butterflies and yellow flowers. Okay, so the prediction based on this hypothesis forms the basis of an experiment that we can do. So we say, okay, if we do an experiment where we give the butterflies an option to land on white flowers or yellow flowers, we predict that they will land on the yellow flowers. Okay, and the last set of skills are used to create an experimental model. Now, this is the last in the progression. So the experimental model builds upon the explanatory model, which was built upon the descriptive model. So in the experimental model, we use experiments to test the predictions that we made in the explanatory model. So a good experiment should test one variable and keep all other conditions the same in order to avoid confusion about what's truly happening and about what's truly causing the results that we're observing. The text warns us that we have to be very, very careful when we talk about experiments, and that it's often a misconception that's perpetuated that experiments are required in order to, quote, do science. But as we know from what we've learned about the definitions of science in our earlier chapters, experimentation is not a necessary part of doing science. It's simply one method that is used to test predictions. On the other hand, not all predictions can be tested by experiments. So when we design an experiment, a good experiment is going to have the following process skills. It's going to have a prediction. It's going to have identifying variables, the independent, the dependent, the controlled, and potentially the experimental controlled. it's going to require that we interpret the data and define the operational parameters. Okay, so in identifying the variables, the independent variable is the one that the thing under study that we want to test. So in the example of the butterfly, whether or not it will be attracted to the yellow flower is the independent variable. It's the thing that we predicted that the butterfly would be attracted to. So it's the variable that we're testing. The dependent variable is the number of objects that respond to the independent variable. So in this case, it would be the number of butterflies that actually are measured that land on the yellow butterfly instead of the white one. And in any experiment, we need to have controls. And what a control is a way to make sure that all of the other factors in the experiment are the same. We don't want to vary any more factors in the experiment. We want to make sure that we can pinpoint the true source of our observations. And so we need to ensure that we have controls in the system. We need to teach the students methods of interpreting their data after they use the experimental model, how they use the data to compare it with the original question, compare it with their hypothesis, and after they classify the data, and does it actually support the hypothesis that they had? Does it support the prediction that they made based on the hypothesis? And so these are some of the questions that you'll need to teach the students how to answer when they are following the process skills in the experimental model. So this brings us to the end of Chapter 3. And once again, in each one of these inquiry-based process skill models, there is an example of a classroom-based activity that shows this model in action so that you can get a better idea of what the model actually means in real life, in real practical application. So this brings us once again to the end of Chapter 3. So if there are any questions or issues that you don't understand, please make sure that you reach out to me and so that we can discuss any concerns or areas that are not clear to you. Okay? All right.